I welcome. It's your now.
Thank you, Vasant Kumar, for very kind words. I hope all of you are able to hear me well. I think we are already behind by 18 minutes for the day. So I would like to directly go into the presentation. And I was told now that the people who are in the audience are from aeronautical department. In fact, I don't have much of experience in aeronautical composites, even though I have done some work in that. So I may cover other than aeronautical also. Maybe you can apply your knowledge into aeronautical also. Is that my screen visible? I would like to have
Yeah,
acknowledgement.
it's visible, sir.
Okay. So I think there are about 34 slides in my presentation. In my estimate, it should take about 45 to 50 minutes. So I should still be able to catch your timing of 7 o'clock closing. And maybe at the end, I can have 10 minutes for question and answer. If you can have any questions, you can put it in the chat box so that I can read it out at the end and answer them. And FPL and Polymer, I think Vasant Kumar has given a good introduction. Still to run through quickly, Formulated Polymers Limited, that's how the name FPL came. We are into manufacturing of engineering plastic compounds since 1991. We are about 34 years now in the business. And we had a collaboration with General Electric company, a GE company called LNP. And in formulated petrochem, we were manufacturing regenerated sustainable product. FPL Nippon Polymer is the reason one where it is the Indo-Japan collaboration joint venture where we are into composite. Thermoset composites. Okay, even though thermoplastic composites we were in FPL formulated polymers. Now Nippon Polymer is a thermoset composite. As Vasant Kumar explained, I think we are also into passenger vehicle distribution with about 40 centers. We are in software businesses other than manufacturing. So coming to composite, composite is nothing new. Okay, it was there long ago. For example, 7,000 years BC, itself composite was there. People know to make a house not only in mud and straw brick, so that the straw acts like a fiber to reinforce. And so our past generation had the knowledge how to use them. In 3000, we started using it in plywood to reinforce them. And in 3000, I think composite bows were made. Because that time arrow and bow was the only mechanism of war, and that was made with wood, animal glue, etc., and fiber from plant to make a flexible bow. Okay, so that the arrow can travel longer distance. That was 3,000 years ago. Okay, so composite is a very old process way of combining two materials and trying to get. In 1907, bakelite came in, the first plastic material, and which was used as a composite majorly. And 1935, fiberglass was invented, which revolutionized the composite industry. So polymer composite, what is it? Okay, we are talking about polymer composites. I'm going the very basic thing. It's the polymer matrix reinforced with fiber or filler. So you can put a fiber inside, or you can put a filler inside into a polymer composite. Then it becomes a composite because it is now two materials are there. Polymer matrix is there, filler is there, or a fiber reinforcement is there. Depending upon how it behaves, I'm sure 2 days you have gone through the classes. You know what is the difference between thermoplastic and thermoset. Thermoset is once the heat is applied, it sets. So it cannot be reversed. Like the old bakelite telephone, black color telephone you will know. They are all thermoset materials, once set, permanently set. And thermoplastic is the one when you apply heat again and again, you can melt and reshape them. Okay. So there are two ways you can do that. Okay. But in today's uh, presentation, I'm limiting to thermoset. So for thermoset is where the composites in aeronautical and other applications are happening. Okay. Even though there are some thermoplastic in interiors and all that, but still major ones are coming in thermoset. Okay, the key component, as I said, fiber, which gives the strength. The reinforcement could be glass fiber, it could be carbon fiber, it could be aramide fiber. Aramide fiber is nothing but a polyamide fiber of aromatic ring. And the matrix can be anything. Okay, the whole strength is coming from the reinforcement, whether it is a glass or a carbon fiber. But it has to be retained in some shape. Okay, for that you require a binder or a matrix. So the matrix flows over the fiber in the way we want, and then it sets so that the fiber sets at the particular shape. And when the load is applied, the fiber takes the load, not the resin. The resin is just a binder or a matrix holder. Okay. So this is the basic understanding one should have on composite. The composite, the whole strength for the whole process or the whole application, everything comes from the fiber, okay, or the reinforcement. And this binder matrix is primarily to hold them together, okay. Typical ones are epoxy, polyester, uh, polyimide, and all that, okay. I'm again narrowing down to thermoset. Okay. In thermoplastic, there are many, which is what we need to do it in thermoplastic compounding like polyamide, PPO, PPS, polyphenylene sulfide. There are many polymers are available, okay, in which you can do fiber reinforcement. And the limitation between thermoplastic and thermoset is in thermoplastic, you can go up to 40% or 50% fiber, max. Beyond 30% processing becomes very difficult. So 40, 50 people will process with little difficulty. Whereas in thermoset, you can go up to 75, 80%. So it is primarily the fiber which is going to perform, and the binder is just 10, 15% to hold them together. Okay, so that's the concept. So the major material used for binding is matrix, is epoxy or polyester, which are all two commercial ones. So the most concentrated one is fiber. Okay, and there are many fibers you have. Okay, carbon fiber of all will give the highest stiffness, and aramide gives the highest aberration. Okay, glass fiber is general purpose. Glass fiber is used in many places because it is cost competitive and it does many performance. And carbon fiber is used where you require very high stiffness with a very thin section. I don't know whether you have seen a carbon fiber composite. At around, say, 0.5 mm, you will get a modulus, flexural modulus, what a 5 mm glass can achieve or a composite can achieve. And aramide is used if there is an aberration in the composite. Okay, then aramide fiber don't get aberrated fast. Okay, so in the right you can see the table. Okay, the Young modulus of carbon fiber, aramide fiber, and e-glass. So you can see the carbon fiber can be 10 times stronger, or modulus will be more compared to glass, e-glass. Okay, the tensile strength GPA, if you see, it is around 1.5 times compared to aramide is 2 times. Okay, and density also matters because everywhere we are going to talk throughout the session lightweighting, because the objective of composite is to replace the conventional material like iron, steel, or maybe even aluminum. You all know that steel is 7.8 or 8 density, 8 grams per cc. Aluminum is 2.83, depending upon the alloy. Whereas the composite, as a composite, it will be around 1.7, 1.8. So compared to steel, okay, it will be 5 times lightweight. So if lighter the weight, there are many advantages happens in the product. Okay. So the below one, you can see the lot of strength density map is there for different fibers. There are various fibers available. Here is the density, and this direction is the strength. Okay, so you can select various fibers. Higher the density, higher the thing is metal fibers. Metal fibers also possible. Okay, you all know that in tires we had a steel reinforced tires were there. Okay, radial tires were there. Okay, so and then it got replaced by carbon fiber, then aramid fiber. Okay. Higher the density material also there, lower density materials are there. Okay. So depending upon how we want, we can pick up the fiber uh, from the density point of view, from the strength point of view. Okay, what are the challenges? You selected a fiber, okay, and the fiber should stay in its shape, and the composite, the binder should flow over that. Okay. When it is flowing, it is also should hold on. Okay, they should be mixed up in the sense that the bonding between the fiber and the matrix should take place well. Then only the real composite will have a good strength. If they don't compatible to each other, then you will not be able to achieve the strength that you want. So the most interesting challenge for the chemistry people is how do we, or the polymer people is, how do we bond this composite between the filler or the fiber with the matrix? Okay. Okay, having said, I was just saying in thermoplastic, 30% glass reinforced thermoplastic is a very popular maximum strength. The reason is 30% glass filled glass fiber reinforced thermoplastic is easy to process. If I make 60%, it will not flow. If it flows, it will not give a surface finish. Okay? Glossy surface finish or repaired surface finish will not be available. The glass fiber orientation will change. There are so many challenges. Likewise, in thermoset also, the processing becomes very difficult because how do we do this? And I'm sure all of you are aware of Aerolite in our life. Sometime you have used a soft resin, a hardener. Okay, then we mix both and then it sets. Okay, that is the thermoset. Okay, so you have got limited time. With by the time you can complete the operation and surrounded by the fiber. Okay, the fiber is there, surrounded by the resin. The resin should have two component system. Okay, to cross link and well, cross link you sometimes you may have to apply heat. In aerolite, we do it at room temperature. Whereas in some applications, for like polyester, you have to apply at least 140 degrees centigrade, and it should be penetrating throughout the matrix. Then only the curing will take place inside. Can I continue? Okay. So the processing is a very big challenge. Okay. When I say processing, actually in manufacturing technique is we want consistency. The product, first product, 100th product, 1000th product, 1 millionth product should have the same dimension, same way. The resin matrix shrinks a lot. Okay, it shrinks by about 4%. So if you want to make a 1 meter scale and you make a die of 1 meter and you pour the resin, you will only get 96 centimeters. Okay, the 1 meter will be 96 centimeters. The 4 centimeter will shrink. So when you put a fiber, it may shrink to say maybe 99 centimeters. So, but you require this 99 centimeters always. So you make a mold of 100.101 or 100.98 or 97. Okay, so it shrinks to 1, okay, without machining. So there are a lot of processing techniques are there to ensure that the consistency is maintained in the product. These are all the two challenges. I would like to run through some application for you to appreciate where all it is used in the industry. Since it's an aeronautical thing, let us take the 787 Boeing. Okay. Unfortunately, it met with an accident in Ahmedabad now. Okay. But it was a very safe aircraft flying for more than, it came into picture in 2004. And for 20 years, it has been flying. Okay. And Boeing introduced 787 Dreamliner in 2004. And what is the biggest change they did? They made the most of the airframe from composite, carbon fiber composite. They made it. Okay. So see the table below. Okay. 50% of the Air 787 is composite material. Okay. The gray color is carbon laminated composite. Okay. Most of the things are gray. Okay. You can see it's all made from composite. Okay. And aluminum is also used, some application where they could not replace, but a substantial change. 50% of the aircraft was replaced with composite. Aluminum came next, about 20%, titanium is about 15%, steel is about 10%, others. And if you see the density, because lightweighting is important, composite is about 1.8 gram per cc, aluminum 2.83, titanium about 4.5, steel is about 7.88, and this is much more than 8. Okay, so the idea of what driven Boeing is, how do we make it lighter and lighter? Okay, so that the way the aircraft become more usable. Why it should be lighter? Just see this. Okay, this is the first aircraft which came in 2003, 2004 as a long haul aircraft. Chennai, I mean Delhi to San Francisco, they could fly in without refueling. Okay, even today the Dreamliner does the same thing. That was the first aircraft, the first flight. 17 hours it could fly. Okay, with one fuel filling. So when the engine, when the wings and other things became lighter, they could accommodate little more fuel. That's one way of seeing how to compensate the weight. And second way is that since they become lighter, okay, you burn less fuel to fly. Okay, so it is able to do a long haul flights. Okay, and not only that, it saved about 25% of the fuel. Okay, it was more fuel efficient. And look at for manufacturers like Boeing, 25% fuel efficient aircraft. Okay, commercial aircraft. Okay, it's a very big thing. It could fly 16,000 kilometers. Earlier, the longest range we had was around 9,000 kilometers. So if you are going from here to San Francisco, you will do a refueling in Frankfurt or UK. You will get down, take about 2 hours to refuel and again fly. Okay? Whereas now you are able to fly in one thing. So composite made the difference thing. And here is the statement given by the composite person, okay, who worked there. 20 years ago, he made the statement recently. Boeing engineers predicted the use of composite material in the design of 787 Dreamliner would improve the efficiency, durability, and even the passenger comfort. Seeing the result after more than a decade in surveys, Boeing technical fellow found promises. Whatever we said, it really happened. Okay. I mean, some more data on what happened in Dreamliner. Okay, so Dreamliner comes with 3 varieties. Okay, 787, 8, 9, and 10. Okay, that's how they upgraded it. Okay, all of them had 25% weight saving. What a 25% fuel saving also. What are the 25% fuel saving to a commercial airline? You all know that Boeing makes a good profit. Airbus makes a good profit. But most of the airline which runs, whether it is Air India or you name it, International Lufthansa, Singapore Airline, you name it, all of them make losses. Because in operation of an airline, you don't make money. Okay, whereas the manufacturer makes money. So there was a constant pressure on the operators to improve. And 25% of the airline spending is on fuel. Suppose you are able to save 25% of that, that means that directly you get about 6% extra margin compared to the competition if you are owning the Dreamliner. Look at the weight of the Dreamliner, okay? Because it got reduced, it was able to take off 227 tons as a dead weight. Okay, that is the maximum takeoff weight it can do. Okay, and operating empty weight is about 119. So 119 otherwise would have been around 145 or 160. Okay, so if from 160 it came down to 120, say let's call it off, round it off to 120. So about 40 tons of extra load it can take in the vehicle. Okay, so maximum payload also improved. It can carry about 55 tons of passenger luggage extra together. So the biggest advantage of composite usage in Boeing was it reduced the weight and it improved the fuel efficiency and it gave a good styling also inside the cabin. Okay, and after that everybody started using it. Okay, and today Airbus also uses a large amount of composite in their vehicle. And just see in another application, wind turbine. All of us, we know windmills, okay? And if you are traveling on a national highway, you will see a very large blade running in few 100 meters, 120 meters, being taken on the highway, okay, to install. Assuming that this would have been in aluminum, okay, or maybe in some other metal. This is the weight of a blade, okay, let's take a onshore thing. It is 15 tons will be the weight of each blade. So if you have 3 blades, it's 45 tons. So think of 45 tons to be vertically mounted. What kind of steel structure you should have on the structure which is holding it. And if it is offshore, it is around 35 tons. Each blade is 35 tons. If you would have made it in steel, for example, just for the sake, it would have been 35 into 5 times, about 150 tons per blade will be the weight. Okay, so the amount of wind energy required to push this itself would have got lost. Okay, so composite, which is it's fully made out of glass fiber reinforced polyester. Okay, by hand laying process, and this reduces the weight. And today, we in a span of about 15 years, we started with a very small 50 kilowatt power capacity. You would have seen when you are traveling in a highway, you would have seen small windmills. Today, that has gone. Okay, we are now having 6 megawatts thing from 450 kilowatt. We are going to 66 megawatts. Okay, in one turbine. 18 megawatts are also there. Okay, the large ones are there, and all this was possible because of the composite. The plates were in composites. So there are many things in electric vehicles. Okay, in passenger car, you know that today IC engines and diesel engines are getting replaced with electric vehicles. Okay, and electric vehicles, the biggest challenge today is how many kilometers it will run per charge. Okay? Initially, we started with 100, and Tesla came out with 550 kilometers per charge. And today in India also, Tata makes 550 kilometers per charge. MG makes 500 kilometers per charge. For single charge, 500 kilometers. But if you see the pamphlet, there will be a lot of conditions. For one passenger driving, okay, this kilometer is specified. If all the seats are occupied, that means that assuming a person will be weighing about 70 kilos and 3 more passengers are added, 210 kilos are added. Okay. And 210 kilos are added, the kilometer will drop by around 60, 70 kilos, 70 kilometers. 500 will become 420, 410. So EV is so sensitive to weight. Okay. Today it's so sensitive that we are replacing even the seat. A seat which has got a PU foam, because PU polyurethane is very high dense material. So we are trying to look at whether we can make it in polypropylene foam so that it will become less weight. Okay, they are counting weight in grams in every part of the electric vehicle. So in electric vehicle, composite has made a revolution. Okay, even in otherwise, if you see Ambassador, the old car, and today we are having about 50 to 90 kilos plastic in every car. So what it means to us, okay, 50 to say 50 kilos, if you say density is around 1.2 average in plastic. So it has replaced about 400 kilos of steel. Okay, that's how today we are claiming. Those days the vehicle was giving 6 kilometers per liter, and today it is able to give 24 kilometers per liter. And the safety of the vehicle has improved multifold. Okay, crash load or passenger comfort, everything has increased multifold. Now all the cars are air conditioned. Where the engine is, the power is coming from the engine. Okay, so after all that, also we are still able to achieve 20 kilometers and 24 kilometers. It's all because of plastic, and in that 60% of the car is made from composite. Some reinforcement is there, glass or anything. So it reduces the weight. It improves the thermal stability. It increases the EMI shielding. in EV car, EMI shielding is important, okay? And recyclability. And I'm sure you would have seen the recent Indigo accident happened in Delhi to Srinagar flight. The nose got damaged, and the nose is made out of composite, and that got damaged, okay, for the first time. Okay, it has never happened. And why it should be in composite? It could have been in metal, because it has to have EMI shielding, okay? That the signal should pass through. Okay, if you put metal, the signal will not pass through. Okay? So there are various other reasons why a plastic or a composite is also used here. Okay? In electric vehicles, there are so many places where composites are used. It could be structural or body component. For example, now the government has announced all commercial vehicles, that is trucks, should have air-conditioned cabin. Okay, the driver should not get fatigue. Okay, the government is rolling out from 2027. No truck can be the way the old trucks can be. Every truck should have an air-conditioned cabin. So if we are going to suck some more energy from the engine for cooling the cabin, then somewhere we have to reduce the weight. So what commercial vehicles are thinking is make the whole cabin, the driver cabin, out of composite. So structural and body components are possible. Battery related parts. There are many battery related parts are in composite. Interior components are in composite. Chassis and suspensions are getting into composite. There are many exterior parts, okay, mirror housing, headlamp housing, they're all in composite. Because headlamp, when it was in halogen, sometime back, we had the technology of halogen bulbs in all the headlamps. Halogen bulbs used to generate a temperature of 140, 150 degrees centigrade around it. Okay. And you can't put any other plastic, it will melt. So they have one for a thermostat, okay, which will have the composite. Today it is all in LED, but still in composite, because the specifications are changed in headlamp today. Okay, you should have 1 kilometer range. If a headlamp is on at the time of testing, you should have 1 kilometer. You should be able to sense. Okay, that's a throw they are expecting today from a headlamp. Okay. So this photograph, which is the EV battery cover. So you all know that in commercial EV vehicle, the battery is below your seat. Okay. And we have seen accidents of the battery catching fire earlier, because when we were experimenting the overcharging, fast charging, etc. And today, for that you require a protection. Okay, so you have to cover it up for the human to be safe. So that protection is coming from composite. Why composite again? Because it is lightweight. We will not add weight, and at a very thin section like 1 mm, it will do the job of what otherwise a metal or aluminum will do it at around 3 mm or so. So 1/3 of EV in a electric vehicle, 1/3 of the weight comes from EV battery. Okay, and 2/3 is all other things, tires and interiors and all that. So run depends on the weight. Okay, or run, and I say how many kilometers it will run. So efforts are on, okay, to lower the dead weight. Okay, you want to make it lighter and lighter, the vehicle. So a day is not very far away that electric vehicle will be fully composite vehicle, so that you can reduce the weight. And the same is applicable today. I think we are talking about in aero, EV arrows are there. Even today's Times of India carried some article saying that 170 kilometers somebody could travel through using a EV aeroplane. Okay? The EV aeroplane is fully made out of composite. The drones, which we had used in the war, is fully made out of composite. Okay? Because no metal is used. Because you should have an EMI shielding, and prevent communication also should happen. Okay? So the most happening now is going to happen in India is composite cylinders. Those are all the days when we had a very heavy steel cylinders. And I'm sure all of you would have seen by now these plastic cylinders. These plastic cylinders are nothing but blow molded polyethylene bottle, wounded by composite glass fiber, or and then resin cured, and then there is a box outside that. So it is transparent. You can see the level of the LPG inside, and it is absolutely accident free. Okay, it never explode. Right? At the max, it will happen only the puncturing will happen in the whole product. So this is going to revolutionize thing. Indian Oil has already announced they have started giving this weight thing. Earlier it was in 5 kg alone. Today 15 kg is also available. So I have shown some of the application for you to extend your imagination in aeronautical industry to where all can be used. Okay, how much possible to be used. So some of the recent trend is what is trending is what is pushing the composite industry is lightweighting. And how do we increase the strength? How do we keep increasing the strength so that we can reduce the thickness, we can reduce the part dimensions so that lightweighting happens. Nano reinforcement. Okay, one solution is put a very fine particle, fine nanoparticles into that. It will give you the strength. It doesn't because in a composite, the fiber or the glass is 2.8 density. Okay, and the resin is only 1.3. Okay, so the combination gives you 1.8. Okay, suppose you are able to lower this fiber density, then there is something there. If some researchers are attending this program, this is one scope available. Okay, constantly looking at what are the other fibers which are possible to be done. Okay, and of course, in thermoset, the biggest challenge is recyclability. But there is one set. Okay, we cannot reuse that. So it is becoming a very big concern. Okay, what will happen after some time? You would have seen in many windmills down south or down in Gujarat. Okay, they are not running because they are all 20, 25 years old windmills. Okay, what will we do with a blade which is made out of a non-decomposable material? Okay, so there's a big concern now today is to see how to make it sustainable. Okay, there is another big scope for research or work to be done. Nanocomposites, it could be CNT, carbon nanotube, or graphene. Okay, there are so many small particles thing which will give the strength at maybe a 10% usage itself, what and otherwise you will require 10 times the more material. And we can enhance the mechanical property, we can increase the thermal properties, like for example, aero industry. It has to fluctuate between plus 60 and plus 70 and minus 60 degrees centigrade. Okay. So how do we thermally handle the product? Okay. When you are exposed to this kind of shock in a span of say about 5 minutes or 3 minutes, you are exposing to that thing. There are barrier properties. So bio-based composites are another thing which is going to come up. Okay, the reason is, okay, I can't make the whole things sustainable, but at least can I make some of them? Like I will use the fiber instead of, I'll go back to the olden days and use jute or any organic fiber, which after the usage, if you discard, at least it will get decomposed. You will form an honeycomb structure. Okay, the resin may stay and the resin may collapse. Okay, after some time. So natural bio is another thing. Okay, why only fiber is bio? The compound which is going to hold the fiber can also be bio. Okay, so there is a good potential for future. Okay, how do we invent this biodegradable? Or at least today I will apply heat and I will lock, and I will apply some heat or chemical or something like that so that it will de-link and it will become a monomer again. Okay, this is the research which is going on. Some commercial products are also available in this. Smart composites are another trend which is happening. What is smart composites? Self-healing materials. Self-healing materials is material which will, if there's a crack happens in an airline or airplane or something like that, in a drone, it will heal by itself by releasing some material and fill up that gap. Okay, and it could be for a cut, could be for a crack. Okay, so self-healing materials is another area of work. Shape memory materials. Okay, it will remember the shape. Okay, so you can apply load, it will de-shape, but when you remove the load or heat or a light, it will come back to its original shape. Okay, the trigger can be anything. It could be heat, could be light, it could be electric field. Okay, I will change the shape and I'll bring it back to same. There are many applications which want this. So applications are in medical equipment, medical and aerospace. Additive manufacturing, there's another research area. Okay, additive manufacturing 3D printers have come into metal and then into plastic, but in composite is still not entered because we don't know how to put a long fiber into this and the resin. Okay, but there are some 3D printing technologies that are coming up so that we can make prototypes much faster. Okay, if you want 2 part, 3 parts prototype, how do we do it? Okay, payload structure and continuous fiber is going to be the biggest challenge. How do we do it in that? So conductive composite. Okay, there's another area where big requirement is there, electrically and thermally conductive fillers you use so that it becomes a conductive part. Because metal is conductive, whereas moment I put carbon, not carbon fiber, glass fiber and resin, it become insulative. Whereas I may require a thermal conductive. I want a heat sink, okay, so that I remove away the heat if it is generated at one place. So I require thermally conductive material. I may require electrically conductive, okay. So carbon nanotubes and other things are used so that it can become a conductive material also. EMI shielding, wearable electronics. And today everybody is having wearable, whether it is a watch, a smartwatch, or this. There are so many wearables have come, okay, where shielding is also required and composite is required. For example, my frame, the glass, I think it is a Ray-Ban. It's a carbon fiber composite, okay, very lightweight, and you can see the thickness is so thin, okay, and it doesn't change the shape like metal, okay. Even if it's like a memory, if I flex it, it will come back to its original shape. So, okay, I said polyester, thermosets, and all that. There are many applications where you have to work at very high temperature. And some of the polymers available are PEK, polyether, ether ketone, polyimide, etc. It could be aerospace, automobile, near engine, or inside the engine, and all that. In fact, a complete engine made out of plastic is also available. Composite is also working in Germany. Okay, and maybe a day will come, it will become a practice that we will injection mold or we will do compression molding of an engine. Okay, so the engine is ready to produce. For you to understand, we manufacture this bulk molding compound. Okay, there are various techniques in which the material can be processed. One of the way of manufacturing this bulk molding compound. That is, we mix the resin with glass fiber and others, and then we give it to the molding section. And molding section will apply the heat and cure it and set the process. Okay, so it is a two-stage process. So I'm just trying to say how a typical formulation will look like. Okay, the thermosetting resin could be 40 to 60%. It could be unsaturated polyester, or it could be vinyl ester, or epoxy, similar to that. A low profile additives, I was saying that the shrinkage is 4%. How do we manage the accuracy? So you put some other non-shrinking material like polystyrene, polyvinyl acetate, PMMA in a small dosages so that it prevents the shrinkage of the material. Reactive monomers like styrene and acrylic monomers, why it should be added? The resin is highly viscous material for the unsaturated polyester. It cannot be handled easily. It will not flow. Okay. To make it flow, you require a monomer. Okay, it acts like a carrier. Okay, at the time of processing, it will evaporate away and go away. Okay, and initiator, which will start the cross-linking process. And fillers could be calcium carbonate to reduce the price, or aluminum trihydrate to create a flame retardancy. That is, when a flame is applied on the composite, for example, in railways today, all the plastic parts, you the most popular application of railway is the bathrooms. Okay, the toilet inside the compartment is fully made out of composite. Okay, and it is flame retardant also. It doesn't burn. Okay, so if there's a fire, it will give time to escape. Okay, And aluminum trihydride is a very good example of using as a flame retardant, because when you heat, it will release the moisture. So the fumes will not be toxic to you. There are other ways like putting halogen and all that, but it will create a toxic thing, or it could be red phosphorus, which will create again a toxic process. Okay, so we should give escape time to the people also. So it could be that a glass bubble, okay, to make it hollow sphere, so that the density is less. Color, you can make the colors you want. Okay, mold release, because when you are molding it, you should be able to come out of the mold if it doesn't have a slope. And thickness, thickener, for example, sometimes we have to thicken the part so that it is easy to handle it instead of solution. It could be carbon fiber or a thing 25%, 30%, so that you improve the strength. So these are all the parts which is going to it. This is another area where you can do various research. Okay, that additives can be different, the formulation can be made from different materials. Each has got a different advantage and so what will be the future will be? The future still will look for lightweighting. Okay, even though composite is 1.7, 1.8 density compared to the nearest competitor, aluminum 2.8, still people wanted to make it lighter. For example, in tractors, the metal parts are gone and people are trying to replace it with composite now. They don't want even 1.8. They want still lower than that. So 1.25 is the target in which the industry is working. Okay, how do we make it still lighter? Okay, and optimizing the FEM, finite element, and AI tools. How do we generate them faster? I said about how the compound application we have seen, what a compound is, how it is made, and all that. Okay, some of them. And the biggest problem is composite processing. Okay, it's a very tough material to process. That's why in plastics, only about 3% of the plastics are thermoset. 97% are thermoplastic. Okay. Why thermoplastic? Because it is recyclable, easy to process. Thermoset is very difficult to process, so we have to make it as light as possible. How easy to do it? The goal is very simple. Goal is a fiber is going to give you the strength. And the fiber orientation, because if you put the fibers in one direction, and if you pull it, it will give you strength. If you pull it like this, it will not get the strength. So how do we position the fiber and pour the resin over this? Okay, this is where the processing is going to be. Okay, this is the simplest way to explain that what we should do. So various ways the goal is achieved. The fiber orientation is maintained, the resin is poured over that. Okay. And of course, volume of production, strength requirement, shape, size, etc. also decide how to process. Okay. Okay, I have a very difficult shape, or I have a very difficult size. Today, metro trains are running in almost most of the cities in India also. And all the parts inside, the panels, the seats, and all that, they're all in composite, okay, because of lightweighting. And they are very big part. So you can't do a compression molding or a injection molding of that part. Okay? So there are various techniques by which the glass is or the fiber is kept and the resin is poured over that. Okay, so there is a huge research area scope is available in this. How to keep the fiber and how to pour the resin around that. Okay, and most of the process are two stages. Okay, it is never done in one go. Okay. It is manufactured as a compound and then applied heat and cured, or it is processed as a prefab and then brought here and then finished at one place. Okay? So processing composite is a challenge. The goal is the fiber has to be kept inside. 70% of the fiber, 30% of the fiber, how do we going to keep it? Okay? There are some advanced techniques which are coming into composite. One is RTM, resin transfer molding, pultrusion and autoclave. Okay. So how do we apply the heat? We make the shape, put it inside an autoclave. Okay. Apply the steam pressure, cure it. Okay. So that you get the part. Pultrusion, it's a continuous product. I keep pulling it. For example, you see all the high tension wires which are running in our 440 and 11 kVA high tension wires. Okay. They are separated by the pultrusion rod. Okay? The pultrusion rod is nothing but a composite where the glass fiber is there, pulled through a epoxy and cubed. Okay. RTM is what is used for this metro train example, which I said. The large parts are made in RTM. Okay. Automated layup and robotics. Robotics also come in so that does the repeated jobs. Okay. So instead of reducing the part. This is a typical RTM where the molds are there. You create a fiber as a honeycomb or the way you want the fiber, keep it inside, pour the resin, close it, it's in the closed mold, apply the heat and cure it, okay? So the fiber doesn't move, fiber stays in the way you want, so that you get your required strength. Another way is for pre-peg production. Okay, pre-peg goes, you manufacture in a factory, in some orientation the fiber and the resin, but don't cure it fully. You do 10% curing and 90% you give it at the application time. Okay, it will be kept inside a press where it can be compressed into aircraft dome, okay, or a nose, and then it is applied heat and cured. I think I'm slightly running out of time. I think I'll close it. Environmental impact. Yes, recycling is going to be one of the biggest strategy for this. If somebody can find a way of recycling composite, I think there are a lot of billions of dollars waiting for that person, okay, to get things. Mechanical and there could be mechanical recycling, there could be chemical recycling, and LCA of the polymer composite, okay, life cycle. How do we extend the life cycle? And end of the life cycle, what do we do? And I'm sure you would have seen the Ahmedabad 787 crash tail being taken by a truck. Okay, it was a very famous photo in WhatsApp and social media. Okay, what are they going to do after investigation? How do they are going to dismantle it? Okay, it should not become an earthfill in some place. So environmental impact and sustainability is going to be a major impact. And there are a lot of challenges. Of course, you can come with wonderful golden fiber, but nobody is there to pay you. Okay, it has to compete with the existing aluminum, or maybe better than that, or so cost is always a thing. And processing should not be very difficult. You should not come out with a process which is very, very difficult to process. Environmental and regulatory concerns are increasing. Okay, 40 years back there was no regulatory concern. Today there are so many regulatory concerns. If you are planning to start a composite industry, the pollution control board will give you a red flag first. They will say, what are you going to do with your waste? What you are not able to dispose? Tell me a disposal plan. Are you going to put it in a cement factory furnace and burn it? He is not going to accept, because he says there are only 15-20% resin in that which is going to burn. The balance 75% is all fillers and glass fiber, which will not burn for me. So for me, the ash will become more. So you have to pay me to dispose this. So there are a lot of regulatory concerns are happening. So there is a big challenge in this also to grow. Okay, the future direction, AI-driven design. Okay, will make the things faster. Multifunctional composites are coming. Okay, there's a show called JEC show in Paris, happen every year, only on composite. And every displays take place on JEC show. And today people don't use only one resin, one fiber or nothing. They connect everything and then they make a composite thing. Okay, different polymer, different thing, but all in one go. Okay, the greater focus is happening in sustainability. Everybody is concerned about sustainability and how we are going to achieve this sustainability. So with this, I come to an end to say that composite, as I said, is about 6,000 BC old material or process, and continuously evolving material science product. So there are a lot of scope to improve, and the improvements are happening in multiple areas. So some of the areas where future works are possible is fiber type and formulation. You can make it still thinner and thinner so that the fiber will give more deliverable. Binder usage, the resin can be different materials. The additive to protect the resin from heat or from UV lights and all that. Enhanced property, life extensions are possible. end-of-life sustainability and waste handling. These are all areas where there are a lot of work can be done in this industry. So with this, I slightly overrun by 7 minutes. I am open for a question and answer. Do we have any questions in the chat box?
Yeah, sir. Participants, if you have any queries, the sir has actually more than 4 decades of experience. Not only how to make polymer or composites, how to put industry and because. So any question actually for the next 10 minutes we can have.
Yes, Mr. Vinod Kumar, you are asking a question. You are on mute.
It was really a very informative and interactive session, sir. I really engaged with this presentation, sir. Sir, I'm a faculty in Polymer department in Kanpur, sir. HBTI Kanpur, sir.
Okay.
So I was asking a simple question whether because I missed few of your slides initially because I was coming back to my home from the department. So just I want to confirm whether do you provide that summer internship for the third year students? Is it possible in your company? Like the people, the BTech students who are in the third year, means the students who are going in the fourth year after giving their exam. Is it possible for them to for like 2 months or 1.5 month training is possible or something?
Yeah, I have two answers for this. Yes,
Sure.
our company can give it, but
Okay,
more
sir.
than that, I am a part of Indian Plastic Institute, where 3,000 professionals are members in Indian Plastic Institute. We have
Okay, sir.
14 student chapters. Okay.
Okay, sir.
So wherever polymer courses are run, we are opening a student chapter. Okay, for no cost. Okay, nothing in that.
Okay, sir.
Okay.
Got it,
Our objective is only three things in that. Okay. Number one, we bring faculty to you. Industry people, we bring it to the institute. Okay.
Okay, sir.
A
Okay, got it.
foreigner who comes to India or something like that, we bring it to you. Okay, number one.
Okay, sir.
Number two is when you want internship, we arrange internship for all your students, not one or two.
Okay.
You
Okay,
give the
got it, sir.
list. You give the list. In Kanpur itself, we'll be able to locate. We'll be able to locate in UP. We'll be able to locate in Delhi. Okay.
Got it, sir.
We will arrange our thing. We have about 1,200 students. Okay. Last year
Got
we
it.
gave for 250 of them. They requested for internship. We arranged. Okay.
Got it, sir.
SIPPAT, we are arranging internship for them. Okay.
Mhm.
So SIPPAT is running our student chapter in about 7 locations or so. So if you are interested, try to reach us out in Indian Plastic Institute. We'll be only happy to connect you to our Delhi chapter. Okay.
Sure, sir.
We have 14 chapters all over India. Okay.
Got it,
So
sir.
Delhi could be the nearest one to you. Okay.
Mhm.
So where we can connect you to the chairman and you can create a student chapter. We'll help you out with a student chapter creation. And
Got it,
then
sir.
we will do this. And then the third one is whenever the Plastic India exhibition happens, for the
Mhm.
student chapter students, we are giving two-way train ticket,
Got
okay,
it,
to
sir.
Delhi, okay,
Mhm.
wherever they are, whether it is Kanyakumari or Calcutta, we provide them a two-way
Okay.
thing. And for the faculty, for the air-conditioned thing, okay, we bring them there, okay, we allow them a free entry into the exhibition for them to see. The whole objective is we want to retain the polymer trained people in our industry and we don't want to give it to computer industry.
Yeah. Thank you, sir. Thank you. Yeah, because the thing is that, sir, I have joined this department last year, sir. So the thing is that I have seen that most of the students are going, means that previously that their seniors are going in the same company. This batch is also going in the same company. So what I was thinking that instead of going in the same company, they should go in other company also. So that they can learn more how the means
No,
and it
you
will
can,
be.
at FPL we can give it, but I can also help you out. The student who doesn't want to travel beyond UP also, we can arrange inside UP also. As I said, 3,500 members or members of IPI, okay, Indian
Yeah, yeah.
Plastic Institute. So we can request any of the 3,500 members to accept the student. Okay.
Sir, first
And
of all, I will become a member of this Plastic Institute. Then later on, I will start the chapter in our campus. So it will be better
Sure.
for us also.
Sure.
Thank you, sir. Have a good day.
Okay.
Welcome, Mr. Manish.
Thank you, sir.
Okay. So before the next question, sir, actually I can request you to see your. I sent one message through WhatsApp. That is regarding our through WhatsApp your personal WhatsApp, sir. Regarding IPI, actually our IPI Chennai chapter is conducting one for students of polymer engineering, actually a competition where actually the prize money is around 25,000. You can tell that also. I sent you the message.
Okay.
Yeah, I think there are many activities we are doing it in IPA, okay, for the interest of this industry. Okay, one of the things is we have a competition on blow molding and material, okay, sponsored by one of the members, Poly in general or somebody. Okay, the prize money is much more than that, not 25,000, it's much more than that to give them entry, but I think the deadline is approaching it. Okay.
Yeah,
So,
August 5th, sir. August 5th now is last
okay,
date.
last.
Yeah.
So you can become a member. You will get all these updates, and you can encourage your student to become member so that they are connected with industry. They get the confidence that they belong to industry which is very large, and there are a lot of people to help them.
Okay.
Okay, and give the hand.
Thank you. Thank you, sir.
Welcome.
Any other question from participants? So on behalf of Department of Polymer Engineering and Aerospace Engineering of V.S. Abdur Rahman Institute of Science and Technology, because you spend your valuable time, sir. Actually, thank you so much for coming and updating. Actually, gave your views, and I think hopefully many people actually updated regarding the things. Thank you so much, sir.
Thank you, Basant Kumar and Abdul Rahman University and the madam, okay, for inviting me. And I hope I added some value and knowledge to you to what direction you can go. I wish good luck to all of you. Thank you.
Okay. Thank you so much, sir. Okay. Sir.